Hello everyone, welcome to Math 115, College Algebra. So in this last section, I want to talk a little bit about an application that's very useful, an application of trigonometry that's very useful for physics, engineers, mathematicians, and that's the concept of a vector. Okay, so let's start by talking about graphically what a vector looks like the geometric view of a vector. You can think of a vector as basically just an arrow, right? Or a ray or a directed line segment where we have an initial side, or I'll say an initial point, and a terminal point. And the vector is drawn like an arrow from the initial point to the terminal point. So this is an initial point. That's like the tail of the vector, and the head of the vector is at the terminal point. Now you can label these points, and definitely mathematicians and engineers and physicists have different notations for vectors, but let me try to stay with the notation that that'll be used in my math. So let's call this first point P, the initial point P, and the terminal point Q. Then this vector you can write as PQ, and you put an arrow over it to represent the fact that it's a vector. Okay, but the other notation is just to give it a name. Like, let's call this the vector V, and then again putting an arrow over it represents the fact that it's a vector. So in this case, the PQ is the same as V. I just named it a different name. I gave it the name V in this case. The way that we represent a vector in terms of its components, because this is what's considered a two-dimensional vector, and when we start drawing them in our Cartesian coordinate system, it's going to have an x component and a y component. Usually, the way we write that, at least mathematically, is we use an angle bracket, and then the first value, I'll just call A here, is the x component, and the second value is the y component. So this is the x component. So x component of the vector, of vector V, and this is the y component. Of the vector V. Okay, sometimes we even just call this Vx, like V sub x and V sub y, meaning the x component and the y component. And notice here that the vector has both a magnitude, which is given by the length of the vector. Okay, so the magnitude here is given by the length of the vector. And it has a direction depending on how it's pointing, right? And actually, we will define the direction later. Again, when we have a coordinate system, we will define it by an angle. So the angle will tell us the direction. So it has a length, right? A magnitude given by the length, and it has a direction, which is going to be given by the angle. Okay, let's look at an example. First example, consider the vector whose initial point P is at 2, 3, and a terminal point is at 6, 4. We want to graph that vector, and then we want to graph the position vector, and a position vector is the same as the original vector, except it starts at the origin. Okay, it'll have the same magnitude and direction as the original vector, except it starts at the origin. So let's actually make a coordinate system here. So let me draw that straighter. So there's my y-axis, this is my x-axis. Okay, so the original point is at 2, 3. Okay, so 2, 3, right? That's the initial point, P. This is at 2, 3. You can think of this, if you want, as x1, y1. And then the final point is at 6, 4. So let's say 6, and then up 4. It'd be like right here. So this is Q, which has the coordinates 6, 4. And I'll think of it as x2, y2. So the vector is going to be going from P to Q, right? From the initial point to the terminal point. So it'll look something like this. Okay, what are the components of the vector? Well, for the components, right, I can basically, because I'm in a Cartesian coordinate system, I want to find how much is moving, how much of that vector is in the x direction, that's the x component, and how much is in the y direction. So the way to think about that is in the x direction, I'm moving from 2 to 6, right? So this length right here, if I move just along the x direction, that must be of length 4, right? And you can figure it out by computing x2 minus x1, right? So let me write that here. So to find components, so for the x component, I can calculate x2 minus x1. So that's going to be 6 minus 2, which is 4. And then for the y component, I want y2 minus y1. Well, in this case, that's going to be 4 minus 3, which is 1. Or from the picture, we can say that it goes up 1, right? It goes over 4, up 1. That'll be the vector. All right. What's special about a position vector? Because it says draw the position vector. So the position vector starts at the origin. So I'll write that here. A position vector starts at the origin, right? So basically at 0, 0. And it has the same magnitude and same direction as the original vector, PQ. The same magnitude and direction as the original vector, in this case PQ. Okay, I can call this vector PQ, right? It's going from P to Q. There should be like an arrow there. All right. We could also name it V if we want, right? We could call this like V or something. So let's draw the position vector. So the position vector is going to start at the origin. And again, it's going to have an x component of 4. So I'm going to move 4 to the right and then up 1, a y component of 1. So it's going to look like this. I will call that B. We'll call them both B. But I'm shifting it so that the initial point is now at the origin. Then it has the same thing. It has an x component of 4 and a y component of 1. Right? If you look at this projections, this length is 4, this is 1. Okay, and then finally, if I want to write that vector V in component form, it's going to be equal to, so I have my angle brackets, right? The x component is 4, and the y component is 1. This is like my A and B, or Vx and Vy in this case. All right, let me do one more drawing here to explain this a little more carefully. Make sure you understand what these components are. The components are basically projections of the vector onto the x and y axes. So if I have some vector, right, I'll just draw it in the second quadrant for this case. So let's say it's a position vector. I'll call it A. And I want to find the components. Then what I would do is I would drop a perpendicular onto the x-axis. So this distance right here, which is going to be negative, would be my x component of A. Then I would drop one onto the y-axis. So it would look something like this. So I'm drawing a perpendicular to the y-axis. And this component right here is my y component, which I usually call AY. And the sign is important. In this case, AX would be negative, AY would be positive. Okay, so that's what we mean by components. Now in our example, because it was in the first quadrant, the vector, the x component was positive, right, 4 to the right, and the y component was also positive. Okay, so in this case, we were saying Vx is equal to 4, and Vy is equal to 1, both positive. All right, how do we find the magnitude and direction of a vector? Let's say we're given a vector. So in this picture here, it has components A and B, right? And you see that here, how it's written, right? With the angle brackets, A comma B. Remember, A is the x component of V, of the vector V. B is the y component of vector V. By the way, sometimes in the textbook, if they use boldface, that represents a vector. That's why it doesn't have an arrow over it. Boldface means vector V. All right, so how do I find the magnitude and how do I find the direction? Well, the magnitude, again, is just the length of the vector. And to find that, we're going to use the Pythagorean theorem. Okay, so for the magnitude of V, by the way, you can write that several different ways. So magnitude, sometimes people use like double vertical lines for magnitude. It means like the norm. Or sometimes you can just use a single vertical line for magnitude. Or you can just use the V with no arrow, right? No arrow on top. All of those mean the same thing. They all mean the magnitude. And it depends on what book, what resource you're looking at. So again, it's just the length of the vector, right? And if you notice here, we basically have a right triangle, right? If I project this down and then project this over, this is going to be the x component. And then this is the y. So this is like Vx. This is like Vy. But Vy is the same as this distance as well, right? So this distance right here is also Vy. But you project it onto the axis. So I project down to the x-axis, that's Vx. Project over to the y-axis, that's Vy. Okay, so notice here that I have a right triangle, right? I have a right triangle I can extract. I'll do that here. Let me do it in black. Where I know the length of the two sides, right? The Vx, which we're calling A in this case as well, is equal to 4, right? So this length is 4. And the Vy, which is also called B, is equal to 2. So I want to find the magnitude, right, which is V here. So how do I find that magnitude? And then later I'll find the angle theta. Well, just use Pythagorean theorem, right? We know that in this case that a squared plus b squared is equal to c squared. But a is really vx squared. B is vy squared is equal to v squared. So that means the actual magnitude v is going to be the square root of vx squared plus vy squared. Or you could say a squared plus b squared, right? Because actually the way they give the vector here, they give it as a comma b. But that's the same thing as triangle bracket vx comma vy, triangle bracket. Okay, so again, nothing more than Pythagorean theorem. So if I plug in, this is going to be 4, vx is 4, right, or a is 4. So 4 squared plus 2 squared. And if you work that out, this is the square root of 16 plus 4 is 20. So that is going to be my magnitude, square root of 20. And you could estimate that, get a decimal value if you wanted to. All right, so that's the magnitude, right, the length. What's the direction? The direction is given by this angle theta here. How do I find the direction? Well, I could use trig. I know that usually we use tangent, right? I know all three sides now. I could use any trig function. But if I use my original vx and vy, or my original a and b, which are the components, I definitely know those, right? Because those were given at the beginning. And notice here that the vy is my opposite side and the vx or the a is my adjacent side. So I know that tangent of the angle is equal to opposite over adjacent, right? So it's going to equal vy over vx. Or we named it b over a, right? You can use either. But I don't really want tan of theta. I want theta. So how do I get theta if I have tan of theta? That's when you have to use the inverse function, right? Remember, we talked about this way back when we talked about functions. If I have a function of x, and if I take the inverse function of that function of x, it gives me back the input x, right? It kind of like undoes the function. So in this case, the way that we write the inverse function of tangent is something called tan to -1, right? So that means inverse tangent, or some people say arctangent. If I take the inverse tan of theta, and then whatever I do to one side, I have to do the other side. So I'll do inverse tan of vy over vx, or b over a. I'll just write it as b over a right now. Well, the left-hand side, right, so inverse tan of theta, that's exactly like this. It's inverse function of the function of x gives me x. That gives me theta, and that's what I want. I want theta. Most times people don't even write this, right? They just immediately go to inverse tan, but that's really what you're doing. You're taking the inverse tangent of both sides. And then the right-hand side, you'd have to estimate this using a calculator. So we have inverse tan of b, which is 2, over a, which is 4. So inverse tan of 1/2. And if you estimate that, you're going to find this is about, so theta is about 26.6 degrees. Okay, so that gave me the magnitude. So the length of vector v was square root of 20. And the direction, the angle theta here, is about 26.6 degrees. Okay, so knowing that, right, again, use Pythagorean theorem to find the magnitude, use inverse tangent to find the direction. Let's see if we can do some examples here. So find the magnitude and direction of the vector with initial point -8, 1 and terminal point 2, 5. All right, so let's draw this out. So -8, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Okay, so -8, +1 is here. That's my P. And then I want to go to 2, 5. So 2, 5 would be here, right? That would be my Q. So this is going to be, again, let me write out. So the point P is -8, 1. I can think of that as like x1, y1. And the point Q is 2, 5. I can think of this as x2, y2. So the vector is going to be something like this, right? That would be vector PQ. I'll write that again as V. So V equals PQ. Okay. I want to figure out the magnitude and the direction. So, first of all, it's going to have an x component. If I project this onto the x-axis of this length right here. And how could I figure out this length? I could just do x2 minus x1. Right? We can call this Vx. We can call it A. Let's call it A. So this is A. How do I figure out A? Well, it's going to be x2 minus x1, which in this case is 2 minus a -8. So that length is 10, which makes sense, right? If I measure from here to here straight across, that's 10. And then what is the y component? Well, technically, if I project this onto the y-axis, I go back this way, and it'd be this distance, but that's the same as this distance right here. So to figure out that, which I'll call B, I do y2 minus y1. So in this case, this will be 5 minus 1, which is 4. So B is 4, and A is 10. Okay, so now to figure out the magnitude of vector V, which I could just call V, I need to use Pythagorean theorem, right? It'll be the square root of A squared plus B squared. So in this case, it'll be the square root of 10 squared plus 4 squared. And that's the square root of, I guess, 100 plus 16, 116. And then you can simplify this to, if you find if you do the factor tree, right, find the prime factorization of 116, it's 2 times 2 times 29. So this is going to be 2 times radical 29. Oops, 29. And it, or if we approximate it as a decimal value, it's around 10.77. Okay, an exact value. So it depends on whether, this is an important point. Sometimes MyOpenMath will want the exact value, and then you have to tell it 2 times radical 29. Or if they want an approximate value, then you can just find an approximate decimal value for it. All right, so that's the magnitude. That's the length of that vector. A little less than 11, right? More than 10, a little less than 11. What is the direction? So the direction would be this angle right here, right? Theta. So how would I find theta? Well, theta is always going to be the inverse tangent of the opposite side, which is B, over the adjacent side A. So it'll be the inverse tangent of 4 over 10. And if you work that out, it's going to be 21.8 degrees. Okay, and when you give an angle, it's implied that you're measuring from the positive x counterclockwise, which we are in this case, because this vector, if you drew it a position vector, right, so you put P at the initial point at the origin, it's going to be in the first quadrant. So that's okay just to give the angle as is. But sometimes you would add more information, like you would say, if I wanted to be even more clear, it's in the first quadrant, I could say north of east. Right, so I'm starting, if you think relative to east, I'm drawing an angle north of 21.8 degrees. That will give me the angle in the first quadrant. And then, of course, you could always write this in terms of radians, too, by converting, right? If I take 21.8 degrees and I multiply by pi over 180, pi radians over 180 degrees. Then you could also write this as 0.38 radians, right? The angle could be in degrees or radians. We're more used to seeing it in degrees, but it could be either. Okay, another example. Same sort of thing. Find the magnitude and direction of the vector with initial point 5, negative 3, and terminal point negative 1, 2. So again, let me draw a picture. Okay, so 5, negative 3 is going to be like here. So that's my P, which is 5, negative 3. You can think of that as x1, y1. And then the final point is negative 1, 2, which is going to be here. So this is Q, negative 1, 2. This is like x2, y2. Okay, so the actual vector will look something like this. I'll call it vector V again. And notice it's going to have an x component. So if I project this onto the x-axis, it's basically going to be this length right here. And if I project it onto the y-axis, it'll be this length, right? Which is the same as this length right here. Okay. It makes more sense when if you want to be really careful with this, you should probably move the vector so that it's a position vector. So now I'm going to move it so that the P side is at the origin. And then if I draw it, I need to basically have an x component of negative 6 and then a y component of 5. So if you draw it as a position vector, it's going to look like this. And now it makes more sense. If I say the x component, I'm projecting this down onto the x-axis. So I want this length, Vx, which is what we've been calling A, and then this length, which is Vy. Okay, but it doesn't matter. Like the vector is the same. You can move it around as long as you maintain the same length in the same direction. It's the same exact vector. So we can easily find the components in this case. So again, instead of Vx and Vy, let's just call it A and B by doing the following. A is going to be x2 minus x1, right? It's the final x component or final x value minus the initial x value. So in this case, x2 is negative 1 minus x1 is fine. It's going to be negative 6. And that makes sense that it's negative because it's going to the left, right? Again, if you look at when I moved it, so it's a position vector, it's in the second quadrant. So if I project down, that x component is pointing to the left. So has a negative value, in this case, negative 6. And then to figure out the y component, which I'll just call b, it's going to be y2 minus y1. So that's going to be 2 minus a negative 3. That's going to be positive 5. So in this case, this was negative 6, and this was positive 5. So b is positive 5 in this case. All right, so how do I find the magnitude? How do I find the length of this? Well, to find the length, I'm just going to use Pythagorean theorem, right? So the length of v, or the magnitude of v, which is v, is the square root of a squared plus b squared. So v is the square root of negative 6 all squared. You gotta be careful. I'm squaring the entire negative 6 plus 5 squared. And if you work that out, this is 36 plus 25, which is the square root of 61. Okay, and again, that would be an exact answer, but then you could approximate it, right, by plugging into a calculator and getting a decimal value, and it's around 7.81. Okay, so that's the length. That's the length of V. Whether it's drawn there or there, it's the same length, right? Whether you draw it as a position vector or just the original vector. Now, what about the angle? So the angle is really this angle right here. Or it's more clear when you draw it as a position vector. It's the angle that the vector makes with the x-axis, which is really the reference angle in this case. We can use that angle, but we have to be a little careful. If we want to give the true angle and not have to add like north of east or south of west or whatever, we'd have to give the angle from the positive x counterclockwise to the vector, right? Which I'll call phi, that angle. But it's always useful to at least calculate the reference angle first. Okay, and why? Because we just have a right triangle here. It's easy to figure out what that reference angle is. All right, so what is that reference angle? Well, that angle is going to be the inverse tangent of B over A. But you have to be a little careful because we're dealing with a right triangle. I don't want to worry about the signs. See how we knew that in reality the A is negative and the B is positive? Sometimes what people do is they do the absolute value of B over A. Or the way I think about it is I'm extracting out a right triangle. And since it's a right triangle with lengths, then I no longer have to worry about the signs, right? So this length was 5. This length, the component was negative 6, but the length is actually just 6. And then I can find V and then the angle here. So the angle is going to be inverse tan of opposite over adjacent. And if you work that out, it's 39.8 degrees. But here, because we're in the second quadrant, we must add like north of west to ensure that we realize that we're in the second quadrant. Okay? Or if you want to give this angle, I drew it back up here. Let's say I want to give the actual angle from the positive x-axis drawn counterclockwise, the phi here. I could find that. How? By subtracting 39.8 from 180 degrees, right? And that would give me 140.2 degrees. That would be the actual angle. So I can either say, for my final result, I could say V is equal to the square root of 61 at 39.8 degrees north of west. That's enough information. Or I could say V is equal to the square root of 61 at, and if I just give an angle by itself, 140.2 degrees, it's assuming I'm measuring counterclockwise from the positive x-axis. So either of these is okay. Both of them tell me that that vector V is in the second quadrant. These are really vectors now, right? That it's in the second quadrant. All right. What about adding vectors? How do we add vectors? Or how do we multiply vectors by a scalar, by a number? Let's talk about that. Adding vectors and multiplying vectors by scalars or single values. By the way, there's a lot more to vectors. We're just covering the very, very basics in this class. If you take physics with me, we will talk a lot more about vectors. Okay, so the way to think about multiplication here. Let me do this in pictures first. Let's say this is vector V. Okay, so that's vector V. It has a magnitude, has a direction. What do you think 2V will look like? Well, 2V is going to be the same direction as vector V, except it'll be twice as long. It'll look something like this. What about a half v? Well, a half v will be in the same direction as v, but it'll be half as long. So it'll be like this. So a half times vector v. What about negative v? Well, negative v is the same length as v, except it's going to point in the opposite direction. So this would be like negative, you can think of it as -1 times v. So I'm multiplying v by -1. That's the same as negative v. Okay, and then if I could do other ones. Let's say I have, let's say -3 halves v. What does that look like? Well, negative is going to flip it around, and then 3 halves, if I multiply v by 3 halves, it means it's 1.5 times as long. So it's going to point in the opposite direction and be like 1.5 times as long. So something like that. That would be like -3 halves v. Okay, how do we, so that's in pictures, right? It's just going to change the length, and then if it's negative, it changes the direction. What if how do I do this algebraically? Let's say v is given with our standard right angle bracket, and then the x component is labeled as a, the y component is labeled as b. Let's say I want to find some number k could be positive, could be negative, times v. What do? It turns out you just multiply each component by k. So k times v is the same thing as triangle bracket ka. I'm multiplying the x component by k, and then kb, the y component, the b, by k. So you basically multiply each component by k. So that's all scalar multiplication is. All right. So let's do an example of that. Let's say we're given a vector v is equal to 3, 1. And I want to find 3v, a half v, and negative v, and then I want to draw them all on a coordinate system. All right, so let me draw a coordinate system here that we can draw them on eventually. Here, I'll draw the first one. So 3, 1 means the x component is, I'm starting at the origin, right? The x component is 3, the y component is 1, so that's a vector that looks like this. Right, that would be my original v. Okay, what about 3v? Well, first of all, let's calculate 3v. So 3v, now k is 3, right? So I multiply the x component by 3 and the y component by 3. And I'm going to end up with 9 for my x component and 3 for my y component. So that one, I'll draw in blue, means I'm going to go to 9 for x component and y component will be 3. It's basically going to be in the same direction as v, but 3 times as long. It'll look something like that. So that's like 3v. Okay, and then the last one we want, actually 2 more. A half v means multiply each component by a half. So a half times 3 and a half times 1. Well, that's going to be 3 halves, or you could write it as 1.5 if you want, and then 1 half. So what will that look like? Well, that'll be in the same direction as v. It'll be half as long, right? The x component is 1.5 and the y component is 0.5. It'll look like this. It's hard to even draw it there. So that green vector is 1/2 v. And then finally, what is negative v? Well, that's the same as negative 1 times v, right? So it'll be negative 1 times 3, and then negative 1 times 1. So it's going to have an x component of negative 3 and a y component of negative 1. Well, that's going to be the same as v, except it's going to go backwards, right? It'll be in the opposite direction. So the x component now is negative 3, and in down 1, it's going to look like this. So that would be negative v. But it looks the same as v, same length, but opposite direction. Okay, so that's all there is to multiplying a vector by a scalar, by a constant. It either changes the length, and if it's negative, it also changes the direction. Okay, how do we add two vectors? Well, if you want to add two vectors graphically, you have to add them tip to tail. So let's say I have two vectors here. I have vector u, looks like this, let's say, and I have vector v. The way we add two vectors is we start with the first vector, u, and it actually doesn't matter which one we start with, but I'll start with u. And then I move v so that the tail of v is at the tip of u. And I draw v. So I move v so the tail of v is at the tip of u. And then finally, if I draw a vector from the tail of the first vector, so the tail of u, to the tip of the second, that's going to be u plus v. That'll be the sum of those two vectors. Call it, say, like w or something. Let's say we gave it a name. We want w, which is u plus v. Then that blue vector would be our w vector, which is u plus v. So we add tip to tail. Okay, so that's all there is to adding vectors. You always just add tip to tail. Again, if you take a physics class, you will learn a lot more about that in the physics class. Now, how do we do this algebraically? Well, we basically just add components. So let me draw this out. So let's say, let me give particular values for u. Let's say u has an x component of 2 and a y component of 3. And then v has an x component of 4 and a y component of negative 5. So if I want to find u plus v, I'll even write this as, this would be ux. Oops. So this is like the x component of u. Ux is the 2, and then the uy is the 3. And for the v, the 4 is the vx, and the vy is the negative 5. So u plus v is going to be another vector in which you add the x component. So it'll be ux plus vx, comma, uy plus vy. So I'm adding the x components together. So it'd be 2 plus 4, and I'm adding the y components together, 3 plus negative 5. So in this case, remember we're calling this w, right? So w is going to have a final answer of 6. 2 plus 4 is 6, and then 3 plus negative 5 is negative 2. So this would be like the x component of w is a 6, and the y component of w would be the negative 2. Okay, so to add vectors algebraically, you literally just add the components together. Okay, and then subtraction actually is similar, except usually what we do is we think of, when we subtract something, we think of adding the opposite. Just like with real numbers, right? if I had, say, let's say I had -3 minus 5. We immediately turn that subtraction problem into addition problem, right? We write this as -3 plus the opposite of 5, which is -5, and that will give us -8. So we turn a subtraction into an addition problem. Same with vectors. If we start with u minus v, we want to find u minus v, so we want to subtract them. We immediately write that as an addition, u plus, and then what am I adding? I'm adding the opposite of v, which is -v. Right, or -1 times v. Since I know how to add vectors tip to tail, I know how to add them algebraically by adding the components. I literally just add the opposite of the second vector. So I have to change the second vector. I have to multiply both the components by -1 of that second vector. So, for example, let's say u looks like this. And it has components, let's say 3, 3. Okay, so has an x component of 3, a y component of 3, right? Over to 3, up 3. And then let's say v looks like this. It has components -2, right? Because I'm going to the left 2, and let's say up 1. So -2, comma 1. Right? So again, this is like ux, uy, and then this would be vx, vy. All right, and I want to find u minus v. Well, first I rewrite that as an addition, u plus opposite of v, -v. Well, what is -v? -v, remember, is -1 times v. How do I find that? Well, I multiply each term in v by -1, right? Each component is multiplied by -1. So -v is going to be +2, -1. It basically just switches the sign. See how it switched that to a +2 and switches that to a -1. If you were to draw it, it'd be going the opposite way. It'd be the same length as v, but going this way. So now it has a positive x component and a -y component. Okay, but now it makes it easier to add, right? So now I can add these analytically or algebraically. So remember, this is 3, 3. I want to subtract v, but that's the same as adding -v, and -v was 2, -1. So now if I add the x components together, so the 3 and the 2, I'm going to get 5. And if I add the y components together, 3 minus 1, I'm going to get 2. So that would be the subtraction. If you want to do this in terms of a drawing, right, you could start with u. Let's see if I have enough room to draw it here. And then I want to add -v. Well, -v looks the same as v, but it's going opposite direction, so it looks something like this. And that would give me what I really want, which is u minus v, right? U plus -v is the same as u minus v. So that would be like that blue vector. And it has an x component of 5, a y component of 2, right? So x is 5, and it's up 2. Okay, let's do one more example. So now we're given two initial vectors, right? We're told we're given u is 3, -2. And v is negative 1, 4. And we want to find the vector w is 3u plus 2v. Okay. Actually, let's graph these as well. So I'm going to graph these over here. So 3, negative 2 will look something like this, right? So 1, 2, 3, negative 2. So u is going to look something like this, right? It'll be in the fourth quadrant. Oops, a little further over, like that. So this is u. And then v, I'll draw a little lower, say right here. It's negative 1, 4. So I go to the left 1 and up 4. It's going to be in the second quadrant like this. Okay. Ultimately, I want to find w, which is 3u plus 2v. So let's find 3u first. So 3u. Well, I'm going to take each component of u and multiply by 3. So 3 times 3, 3 times 3 times negative 2. So 3u, I guess, is going to give me 9 and negative 6. Okay, if I were to draw that, it would look like this, right? It's basically going to be the same direction as u, but 3 times as long. So it'll look something like this. Right, so this is like 3u. Okay, what about 2v? So I need to figure out 2v. So 2v is take each component of v and multiply by 2. So 2 times negative 1, and then 2 times 4. And that's going to give me negative 2 and then 8, I guess. And if I were to draw that, it's going to be the same as v, but twice as long, right? So now it has an x component of negative 2 and a y of positive 8. So it'll be something like this. Okay, so this is 2v. So same direction as v, but twice as long. And then 3u was same direction as u, but 3 times as long, right? And we drew it in terms of its components. Okay, so now what I really want is w, which is 3u plus 2v. So I already know what 3u is, right? I have that in terms of its components. It's 9, comma, negative 6. And when I add 2v, I already have that answer in terms of its components, negative 2, 8. So now I just add the x components together. I'm going to get 7. And then the y components together, and I'm going to get 2. So if I add this 3u plus 2v, I should end up with like 7, 2. Okay, it's going to be hard to draw this exactly, and let me see if I can get this close. Okay, so I start with the 9, negative 6. That was the 3. That was the 3u. So something like that. And then I want to add 2v. So to add 2v, I need to start my vector at the tip of 3u, and I need to go back 2, right? So I'm going to start here, I'm going to go to left 2 and then up 8. And that will take me to this point right here. So it'll be something like this. So this is adding 2v. So it's, again, it's tip to tail, right? So I start with 3u, I add 2v, and my result is this vector right here. And that's exactly what we got. It's 7, 2, right? So this w here has coordinates 7, -2. Or that's it. I shouldn't say coordinates, it has a components, right? The x component of w is 7, and the y component of w is -2. Okay, so it fits together. The algebraic method matches what you'll get if you graph tip to tail. Okay, again, there's so much more to vectors. This is just a basic introduction. You guys will learn, if you end up taking physics, or in the future ever some engineering or anything, then you'll learn a lot more about vectors. Okay, great, thanks.